Yeah, before we go on to balanced search trees, which I promised in the last class, there are a few topics which are like miscellaneous topic that I would like to cover. And among these, one is the extendable hashing, which I said I would do after I complete trees. Then Lempel encoding, and it's also called Lempel Welsh encoding. Comes from information theory actually, and actually this is used as an alternative to Huffman coding, and for example, the Unix tar or zip actually uses a variant of this encoding algorithm. While Huffman coding ensures that no code is a prefix of the other, Lempel encoding actually looks for something which has already been a prefix to create a new dictionary entry. It's actually you have a hash table of you have a dictionary of code words, here, and you can use a hash table for this, for the dictionary. We'll see why. And another topic is what is called skip this. Basically, we didn't even talk about doubly linked lists. We'll talk a little bit about doubly linked lists. And skip lists actually enable you to have multiple pointers, multiple links enables faster search. Okay, we'll come back to balanced binary search trees after that. So let's start with what extendable hashing is. Most of the topics that I'm covering are from these Markov Weiss, and this is an example from Markov Weiss. So when is extendable hashing used? It's also called dynamic hashing. To some extent on the last assignment you did something that was a little bit dynamic, where the size of the table grew as the number of elements increased, and you had a particular way of doing it. Here, extendable hashing is particularly useful for, actually we will see that even something like B trees use it, when the amount of data is too large to fit into memory, fit into the main memory. That means what we're saying is we have memory. Remember, we create a hash table of size which is 70% loaded if I'm using open hashing. So if n is the number of elements, then you need at least n into 100 by 70. I hope I'm correct. This should be the size that needs to be allocated. Now, if n is very large, then it's possible that the memory, which is, let's say, a few GB, is inadequate. Okay. You can't load the entire table into memory. And further, we also find the amount of data that needs to be stored also changes with time. Typical examples are, let's say you're having some X files in a directory. Now, obviously, every file has to have an address. Now, tomorrow you may increase it to some, suppose you had some way of, so you don't want that sequentially you go through all the files like we did in pre-order traversal. You want that you are able to, so what will happen is alphabetically, whichever is first will be picked up first. You don't want that. So you have something like a hash table which takes the name of the file and finds the location. It's location. Now what you will like is, if I increase the number of files, so one should be able to easily access them. Okay. Access the element. And this is where what we'll do is, so what happens, the data changes over time. Here, one important assumption, not assumption, this is actually done in the context of disks. When you're looking at a hard disk, we assume that the disk is made up of blocks, and I'm sure you're already learning it in your other course, or you'll read it in your computer organization course. And there are M records fit in one block. So you have fixed size blocks. A disk is divided into fixed size blocks. I'll tell you why this is important in the context of hard disk, because you can't partition it into variable length records. Then, because the access uses hardware, and when the records are fixed length, it's always easy to access. Fixed length, it is easy to access. Okay. And so suppose we used open addressing or even separate chaining. What would be the issue? Especially there could be collisions, and the major problem could cause several blocks to be examined. During age of K. Okay. Let's take an example. Let us say, like a hash table of separate chaining. Let's say I have the root here, my main table, which consists of 4 pointers. Okay, 0, 0, 0, 1, 1, 0, 1, 1. And corresponding to the two leading bits, they put data. And what we do is, let's say we have these data items which are stored. And let's say each of these true bits points to a particular block. Okay. And each block can hold 4 records. Okay, so each block holds 4 records. Let us pull these 4 records into it. And that is based on the leading 2 bits that we have here. Leading 2 bits points to the, the data are stored in these record depending upon the leading bits of the data. Let's look at what happens here. So let's say I have some 6-bit data is being stored. 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0. So what is it that we are seeing here? Let me just complete this. 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, triple 1, 0, and triple 1, 0, 0, 1. So each block holds 4 elements or 4 records. Okay, m is equal to 4. So these are the leaf nodes. So this is the root. Root contains 4 pointers, and each leaf stores 4 records, okay, or 4 elements. In each leaf, further, we notice the first 2 bits are identical. Okay. Now suppose we want to insert the record with key 100,100. Then what happens? This will have to be inserted in 100,100. So it has to go into this leaf because the first 2 bits correspond to this block. But this block, what do we see? This block has no space. So let's see how do we do this. So third block, this goes to third block. But third block has no space. Okay. So now what we do is we dynamically split third block so that first 3 bits are used. First 3 bits are used, and we used. Now what will happen? You will get 2 leaves now, 2 new leaves. Okay, let's see how we do this. So that means what? From earlier it was 2 bits which was used now, but because it cannot fit into this third block over here, we need to split this. Once we have to split this, we're going to use 3 bits. So what we do is we split it as shown here. Nothing is changing. Notice that the first 2 bits are adequate to still identify the first, second, and fourth blocks. But now, since we're using 3 bits over here in the third block, we create 1 0 0 and 1 0 1. And this one becomes 0. So obviously, you can, for addressing, you need the same word length. So we extend the address space of the root pointer by 1. 110 and 111. Let's see what happens now. This is a new root now. So what is happening now? This one got split. So notice that the first one still 1 block. Second is also 1 block. And third is also, third now is going to become 2 blocks. Fourth is still 1 block. Let's put the data items back. I still have 0 0 0 1 0 0 0 0 1 0 0 0 0 0 1 0 1 0 0 0 1 0 1 1, and here 0 1 0 1 0 0 0 1 1 0 0 0 1 0 0 0 0 0 1 0 0 1 I think it was maybe third block 1 0 1 1 0 0, or whatever new one that we tried to insert, 1 0 0 1 1. What did it have earlier? It had, what is it that we wanted to insert? We wanted to insert, okay, 1 0 0 1. So this will get into this block. Okay, 1 0 0. And the remaining elements, for example, they're all 1 0 1 0 0 0 1 0 1 1 0 0 1 0 1 1 1 0. This is triple 1 0 0 0 triple 1. So what happens to the parent pointers now? Notice that both of them have the same prefix. So we say these two point to this. Similarly, both these pointers point to this. Now this one points to this one points to this, and both these pointers point to this. So this is what extendable hashing is all about. Notice that we don't rework anything here. We only split that particular record. So notice that we wanted to put one element into the 1 0 record. There was not enough space. So we just split that record into 2 parts and use the next bit, third bit, into also consideration for identifying the record. But you cannot use only for this third bit alone. So we use it for all the other. So we just have to modify the root. And what we do is things which have not been split and the first 2 bits are the same, we make both of them point to the same record, right here. And this is called extendable hashing. And it's primarily used, you learn when you learn operating systems about what's called inodes. And these essentially use extendable hashing for storing records on a disk, which is made up of fixed length records. So fixed length blocks, they're called blocks actually. Blocks. So disk is made up of blocks, and each block can hold a fixed number of records. And when it overflows the particular record, you split that and store the new information. This is what is done in Unix. We'll learn about it more in your